Hi, I'm Brian Waite. My partner Carl Walenciak and I are going to continue our presentation about maritime wind speed prediction using Buoy LIDAR data. You'll remember our previous EDA analysis where we looked at the data, evaluated it for stationarity, and fit some initial models. That's going to be available at a link right below this video, so you can keep checking that out. And we're just going to do a quick review of that material here. If you remember that our problem statement was to look at forecasting wind 10 minutes in advance on a theoretical wind turbine that would be located offshore. You'll remember that the challenge we're trying to address is that wind power ramps up rapidly and can be very random, and so the power grid needs to adapt quickly to incorporate wind in by increasing load or decreasing load, and any sort of forecast that'll help the industry do that would be a benefit. And again, we're using this buoy LIDAR data that is wind collected offshore from a buoy in potential locations where there might be wind. Here you can see our realization of our original data, which is from April 2016. It's 1 day's 24 hours worth of wind data, and you can see it has some strong wandering behavior. Here, though, you can see realizations from 1 to 20 April, and you can really see how much variability there is in the types of realizations that you can get from wind. There's our spectral density and autocorrelation plots. You can see that we've got a peak at 0, indicating some real strong wandering behavior. No real other frequencies that are kind of persistent to speak of, although in doing some additional analysis, we do know that wind can have a diurnal frequency or kind of a daily cycle to it that really only shows up when we are looking at it over the longer term. We can see those slowly damping autocorrelations, and in our initial analysis we had kind of decided that this was could go either way, as stationary or non-stationary. So we did some additional research, and what we learned was that wind can be considered stationary, but only over short periods of time. So if you're looking at a longer period of time, anything more than 12 hours, then you can't really consider wind to be stationary. So we go ahead and treat it for the rest of our analysis as non-stationary. And we include that 1 minus b difference term because of these slowly damping autocorrelations. So fitting that ARIMA model, as I said, we went ahead and took the first order difference and got the result there. And as you can see, it looks pretty white after doing that first order difference, and there's not a lot left to model. But we went ahead and attempted to do AIC and BIC estimate to kind of see what we think the parameters might be. And as you can see, both came up with an MA02 as the primary model, but we know that the MA models don't really represent real-world processes very well. So instead, we fit an ARIMA 2.0, which shows up on the BIC plot. This is our candidate ARIMA model, and you can see the parameters there and the coefficients. And then once we fit that model, we kind of, again, further whited the residuals and had the ACF plot look pretty white. It passed both the Young box test at k equals 24 and k equals 48, although you can see that with k equals 48 it did so just barely. We generated a number of realizations using our model, and this is just a representative example, and you can see how well it mimics the behavior of the actual realization. And the forecast with that ARIMA model was able to achieve an ASE of 0.05. And you can see that the last forecasted value really provides the center for where that forecast is centered around. Fitting a vector autoregressive model, we made use of some of those other exogenous variables that I described: the horizontal wind direction, temperature, barometric pressure, and humidity. We had to do some interpolation of that data because it wasn't collected at the same interval as the other data. Here you can see that the VAR model actually captures the trend of the future data with an ASE of 0.04. And as I explained earlier, I'm sorry, I failed to explain earlier, the blue line represents data from the next day. So we actually had some additional data that we could use as a test set. Here you can see we fit some neural network models. When we attempted to fit the multivariate model with multiple parameters, it took a very long time, and the result we got was kind of mixed. Sometimes it would fit pretty well, still worse than a single univariate model, but most of the time it was much, much worse. And so we didn't have a lot of confidence in our multivariate neural network model, so we stuck with the univariate model. And as you can see, we had an ASE of 0.05, which is on par with the other models, but still, kind of great, not great. But again, you see we're centered around kind of the last predicted value. Now, taking an ensemble model using all three of those previous models, the ARIMA, the VAR, and the neural network, using a simple mean of the forecasts, it actually does an interesting job of capturing the trend here, a little bit of the trend that you can see in the real data and in the test data, and the kind of centering around that last seen value. And maybe that's a good compromise between the two. It does obtain the best ASE on the test data at 0.036. So looking at that all together, we ended up doing some windowed ASE plots on all those same models to get a sense of how they perform more generally on unseen data. And as you can see here, our ensemble model once again really came out the strongest. So in summary, you can see that our analysis with the ensemble model might be the most useful model. The 1 minus b term indicated that the best forecast might be the last seen value, and we need to be cautious of processing time resulting from the neural network model that might not be useful in the real world. And here's some references, and we look forward to taking any questions in the comments section.